So today we're going to look at an introduction to structural member properties. Engineers strive to create safe and efficient designs. When designing a structure, engineers must consider both the material properties and the physical size and shape of the structural components. Two important properties of structural members include the moment of inertia and the modulus of elasticity. The moment of inertia is associated with the shape of the structural member, and the modulus of elasticity is associated with the materials such as steel or pine that makes up the member. Understanding the definitions and calculations for moment of inertia, modulus of elasticity, and today's activity, which involves beam deflection, are important for understanding the study of statics. Throughout the design process, engineers must look for improved ways to build structures and select materials to use in their designs. These materials must be strong enough to withstand forces they're exposed to in any type of environment. Determining the moment of inertia and modulus of elasticity for different shapes is an important consideration for engineers as they strive to make designs much more efficient. Let's begin by talking about the moment of inertia, which uses a capital letter I as its symbol, and it's basically a geometric property of an area that's measured in quad inches or inches to the fourth, and it reflects important information about how the cross-sectional area is distributed about a neutral axis. In essence, the moment of inertia is basically the stiffness of an object related to its shape. All right, so the moment of inertia is the measure of the efficiency of a shape to resist bending caused by loading. Note that the moment of inertia is a section property, and it depends on the shape of the cross-section of the member. The type of material which the member is made from does not affect the moment of inertia. In general, a higher moment of inertia is going to produce a greater resistance to deformation. And resistance to deformation just means resistance to changing the object's shape or size. Let's go ahead and take a look at a few of the moment of inertia principles. Specifically, we're going to compare these two beams. We have beam A and beam B. They're both made of the same material, a wood called Douglas fir. Both beams have a length of 8 feet. Notice, though, that the width and height of beam A and beam B are flip-flopped, and that's because of the orientation of the two beams. Beam A is in the vertical orientation, and we call that beam a joist, and beam B is laying flat in a horizontal orientation, which we call a plank. So for beam A, the width is 1 1/2 inch, the height is 5 1/2 inch. Beam B has a width of 5 1/2 inch, and the height is now 1 1/2 inch. Notice that both areas are identical of 8 1/4 square inches. Let's go ahead and compare these two beams together. What distinguishes joist A from plank B? Beam A and beam B have the same cross-section and length, but the long axis of beam A is oriented vertically, while the long axis of beam B is oriented horizontally. Will beam A or beam B have a greater resistance to bending, resulting in the least amount of deformation, if an identical load is applied to both beams at the same location? Let's go ahead and take a look on the next few slides. So why does beam B have a greater deformation than beam A? Well, it's because of the difference in the moment of inertia due to the orientation of the two beams. For calculating a moment of inertia, specifically with regards to rectangles, you're going to use the formula moment of inertia equals base times the height cubed divided by 12. Your base should be in inches as well as your height should be in inches. If you're wondering what those two subscripts of XX are next to the moment of inertia symbol I, that's just denoting that the moment of inertia for a particular type of object. So just from looking at this formula, you should see why the height plays such a critical factor in determining the amount of moment of inertia for an object, because in this formula you see that it's base times height cubed divided by 12. But you can see that the height cubed is going to be the component of this formula that has a major impact on the overall moment of inertia of that object. So let's go ahead and calculate joist A's moment of inertia. Remember, this beam is in the vertical orientation. So our base is 1.5 inches. Our height is 5 1.5 inches. So to plug it into our formula for moment of inertia, it's going to be base 1.5 times height 5.5 cubed divided by 12. And when I simplify that, I get 21 quad inches. Let's go ahead and calculate beam B's moment of inertia. Recall that beam B is laying down flat, so it's called a plank, and that's in the horizontal orientation, where the base is 5.5 inches and our height is 1.5 inches. So if I plug those two values into my formula for moment of inertia, we get 5.5 times 1.5 to the third all over 12. And if I simplify that, I get 1.5 quad inches. So you can see here that the moment of inertia of these two beams is extremely different. How much different? Beam A is 14 times stiffer than beam B. And although these two beams are identical, just by changing the orientation, we were able to increase our moment of inertia, in this case by a factor of 14. So yesterday we spent a little bit of time talking about complex or composite shapes, which are made up of two or more geometric shapes. And remember, we can take those composite shapes and break them down into much simpler shapes for when we're calculating our centroid, which is the center of the mass or center of the gravity of that object. So as I mentioned before, I wanted to talk to you about why we use different shaped beams versus just using a regular rectangular beam. So let's compare the moment of inertia of three joists with the given shapes. Starting with wood I-beams, rather than dimensional lumber, are commonly used for joist in wood-framed structures. The wood I-beams are constructed using dimensional lumber for the top and bottom flanges and plywood for the web that connects them. Let's go ahead and calculate the area for each of the cross sections of these three different beams. Beam 1 all the way on the left has an area of 10 square inches. The wooden I-beam in the middle has an area of 10 square inches. And then beam 3, which is a rectangular beam again, has an area of 23.8 square inches. Let's also calculate the moment of inertia for each of these rectangular cross sections. In the first picture, again, all the way on the left, the moment of inertia is 13.3 quad inches. The picture in the middle, the wooden I-beam, has a moment of inertia of 130 quad inches. And the picture all the way on the right, beam 3, has a moment of inertia of 178 quad inches. Note that calculating the moment of inertia for composite shapes, such as the I-beam in the second example in the middle, is beyond the scope of this presentation. However, the value is given for purposes of comparison. Just know that there's many online applications that will calculate the moment of inertia for I-beams for you. So after looking at the area and moment of inertia of each of these three respective beams, why do you think the I-beams are used rather than rectangular sections? What is the advantage to using a wooden I-beam rather than the dimensional lumber alone? Note that the first two cross sections have the same cross-sectional area, but the I-beam provides a moment of inertia that's nearly 10 times larger. The I-beam provides a stiffer beam, resulting in a much less deflection compared to the rectangular beam of the same cross-section. Also note that a rectangular joist with the same overall height and width as the I-beam has more than double the cross-sectional area, and therefore the mass will be more than doubled. However, the rectangular section with an equivalent overall dimensions provides only a modest increase in the moment of inertia. What is the percent increase in the moment of inertia? Well, percentage increase equals 178 minus 130 divided by 130 times 100%, which gives us a 37% increase. Thinking back, remember that engineers are always looking for better ways to build structures. Less material typically means that the structures will be lighter as well as less expensive. As you'll explore, the moment of inertia for different shapes is an important consideration for engineers as they strive to make designs lighter and less expensive while maintaining its structural integrity. Let's continue our discussions of structural member properties by looking now at the modulus of elasticity, which uses the symbol capital letter E. The modulus of elasticity is the ratio of the increment of some specified form of stress to the increment of some specified form of strain. In essence, the modulus of elasticity defines the stiffness of an object related to the material's chemical properties. In general, a higher modulus of elasticity produces a greater resistance to deformation. So the higher the modulus of the elasticity, the less the material is going to change shape or size. Now let's take a moment to summarize the difference between the modulus of elasticity and the moment of inertia. Recall that the moment of inertia is the stiffness of an object related to its shape, whereas the modulus of elasticity is the stiffness of an object related to the material's chemical properties. So in essence, the moment of inertia is associated with the shape of the structural member. The modulus of elasticity is associated with the type of material, of what it's made up of, such as steel or pine, as I mentioned before. Now, with a focus on the modulus of elasticity, let's compare these two different beams. We have beam A, which again is made up of a wood called Douglas fir, and now beam B is made up of a certain type of plastic. The lengths of both beams are the exact same. They're both 8 feet, and they're both standing up in the vertical orientation with a width of 1/2 inch and a height of 5.5 inches. The area of both beams are identical at 8.25 square inches, and the moment of inertia for both of these are exactly 20.8 quad inches. So continuing with our discussion of modulus of elasticity, let's go ahead and compare these two beams based off their difference in chemical properties. Do you think beam A or beam B will have a greater deformation or a greater resistance to bending, resulting in the least amount of deformation if an identical load is applied to both beams at the same location? So hopefully you had an opportunity to think about which beam is going to have a greater deformation, and it turns out that beam B will. And the reason is it's because of the difference in the material's modulus of elasticity. One is going to be able to deflect much more and return back to its original shape. We call that deflection amount delta max. When considering the characteristics of objects that affect deflection for delta max, these include the applied force or load to the object, the length of the span between the supports. Think about it. The greater the length of span between the supports, the more it's going to be able to deflect, as well as we need to take into account the modulus of elasticity, the chemical makeup of the material, as well as the moment of inertia, the stiffness of the object in regards to its shape. Now, if you're wondering how to calculate delta max, or the maximum beam deflection, at the center of the span when a concentrated load is applied at the center of the span to a simply supported beam, you're going to use this formula. Delta max is equivalent to the force times the length cubed, the length being the length of the span, divided by 48, which is a constant, times the modulus of elasticity times the moment of inertia. So we got delta max equals FL cubed divided by 48 EI. So let's go ahead and take a look at calculating the maximum beam deflection for both the Douglas fir, beam A, and the plastic for beam B. So let's go ahead and calculate the maximum beam deflection for beam A, which was the Douglas fir wood. The length was given to us as 8 feet. Our moment of inertia was 28.8 quad inches. Our modulus of elasticity is 1.8 million pounds per square inch, and our load is 250 pounds of force. So if we plug those values in to the formula delta max equals force times length cubed over 48 EI, we'll get our answer. The one thing you need to make note of is that the length has to be in inches. So we got to convert 8 feet to inches. So I'll do 8 times 12, which is 96 inches. So if I was to plug all these values into this formula, I would have 250 pounds of force times 96 inches raised to the power of 3 divided by 48 times 1.8 million psi times 20.8 quad inches. And if I simplify that, we get a delta max for beam A of approximately 0.12 inches. So now let's go ahead and calculate the maximum beam deflection, delta max, for beam B, which was made of that plastic. The length is still 8 feet. We'll convert that to 96 inches. The moment of inertia was 20.8 quad inches. Our modulus of elasticity is 419,000 psi, and our load again is 250 pounds of force. So I'll plug those values into that formula. Delta max equals force times length cubed divided by 48 EI, and I get approximately 0.53 inches for my maximum beam deflection for this plastic. So if you compare these two maximum beam deflections for beam A, the wood, and beam B, the plastic, you can see that the maximum deflection of beam B is approximately 4.4 times greater than the maximum deflection of beam A if you do not round the deflection values. Conversely, the modulus of elasticity of beam A is approximately 4.4 times greater than the modulus of elasticity of beam B. Based on these values, you should be able to do a comparison analysis to determine a relationship between the modulus of elasticity and the maximum beam deflection. And you should see that these two are inversely related, which means that as the modulus of elasticity increases, our maximum beam deflection is going to decrease and vice versa.